Welcome to the deep dive. Ever stop to think about why a sticky note actually, well, sticks?
Yeah.
It seems so simple, right?
Yeah.
But the science of how things adhere, how they stick together, it's a surprisingly deep rabbit hole. Touches everything from, I don't know, your phone grip to building airplanes.
Absolutely. We're surrounded by adhesion in action,
Hmm.
often without really giving it a second thought.
Right.
But beneath that, simple stickiness lies this fascinating world of chemistry and physics. Today, we're using the text Adhesion Science as our guide to sort of unpack the core principles.
Okay, great. And for you, our listener, our goal is really to pull out the essential insights from this source.
Mhm.
We want to reveal the fundamental ideas behind adhesion and adhesives, those aha moments that make it click,
Yeah.
and show how this science has real-world impact, all without getting, bogged down in too much jargon. Okay, so let's start simple. What is adhesion exactly?
Well, basically, adhesion is when two different materials join together and then resist being pulled apart. We often call the surfaces being joined the adherend or sometimes the substrate.
Here and substrate, got it.
And for a good stick, the actual sticky stuff it needs to be able to spread out properly, make really good contact with those surfaces.
Like water on glass versus a waxed car.
Exactly like that.
Mm.
That spreading is key. We call it wetting. You want a low contact angle for the adhesive on the surface, meaning it spreads out well.
So it's really about that close contact, that molecular hug right at the start.
Precisely. You need really intimate, close contact between the molecules of the adhesive and the surface. That's what lets the different forces, which we'll get into, really work effectively. And it's interesting. Historically speaking, for centuries, glue was just stuff from nature. Animal bits like collagen.
Right, like boiling hooves or something.
Sort of, yeah.
Huh.
Collagen from skin and bones or plant starches. It really wasn't until the 20th century that synthetic chemistry took over.
Ah.
And that's when the term adhesive became more common, moving beyond just glue.
From ancient Egyptian glues to modern superglues. That's quite a leap. So where do we see adhesives now? Beyond, like, craft projects.
Oh, everywhere, honestly. Think about a simple cardboard box,
Right.
often held together with hot melt glue or maybe vegetable-based glues, sometimes no staples at all.
Right.
Most shoes we wear, unless they're, super high-end handmade ones, rely heavily on adhesives for the structure, the soles.
My running shoes probably have a ton of adhesive.
Absolutely. And bookbinding often uses hot melt adhesives. But it's not just everyday things. Adhesives are critical for, say, bonding steel rails together for train lines.
Wow.
And they play a huge role in medicine, too. Think dental fillings cured with UV light
Yeah.
or the acrylics used in bone surgery.
Seriously. Like bone cement.
Exactly. And there are even stories, maybe apocryphal, maybe not, about cyanoacrylates, superglue, basically being used for emergency wound closure back in the Vietnam War era.
Wow, that's intense. From boxes to battlefields. And it's not just things called glue, is it? Adhesion is hiding elsewhere, too.
Oh, definitely. It's fundamental in so many other places. How printing ink sticks to paper, for instance. Or sealants keeping water out of windows. Paint sticking to a wall. And composite materials, that's a big one.
Like carbon fiber.
Yeah, or think about tires, the steel or textile cords reinforcing the rubber. That's adhesion. Or glass fibers in plastics, making them strong and light. And don't forget nature.
Oh, yeah.
Barnacles holding on to ships for dear life, insects walking upside down on the ceiling. Nature figured out sticking things together long before we did. No nuts and bolts needed.
Nature, the original engineer. So adhesives sound pretty incredible, but are there downsides compared to, say, just using screws or rivets?
That's a fair question. A key limitation is that many adhesives are more susceptible to water and humidity than mechanical fasteners.
Okay.
And their performance can really depend on temperature, based on the specific adhesives.
Yeah, right.
But the advantages are often huge. Adhesives let you join different kinds of materials together, even really thin sheets, which can be tricky mechanically.
Yeah, you can't easily rivet paper together.
Exactly. They also spread the load, the stress, over a larger area instead of concentrating it at points like a bolt does.
Which is good for strength.
Very good for strength and fatigue life. Plus, you get smoother surfaces. Think about a sleek car body panel bonded together versus one with visible rivets. Better looks, better aerodynamics sometimes. And the application process can often be automated, which is great for manufacturing.
Okay, makes sense. So we know what adhesion is, where it pops up. Let's get into the chemistry. What actually makes things sticky? What are these forces you mentioned?
Right. The real magic behind most adhesives comes down to polymers.
Polymers. Okay.
These are basically long chain-like molecules made up of repeating smaller units called monomers. Like, imagine a long string of beads.
Got it.
These long polymer chains give the adhesive its internal strength, its cohesion, its ability to hold itself together.
And they can be different shapes.
Yeah, the chains can be just straight lines, linear, or they can have branches, or they can even be all tangled up and connected, which we call cross-linked, like a net.
Okay.
And these structures affect the properties. Linear and branched ones tend to soften or dissolve when heated or put into solvent, which is how hot melt and solvent-based adhesives work. They flow.
And what about the sticking to the other surface, the adhesion part?
That's where different intermolecular forces come in. Think of them as tiny, invisible attractions between the adhesive molecules and the surface molecule.
Like tiny magnets.
Sort of, but different types. One of the most universal but weakest individually are van der Waals forces.
Van der Waals. Heard of those?
Yeah, they're quite feeble on their own, but they only work over super short distances, like less than 2 molecules wide.
Tiny.
But crucially, you have billions upon billions of molecules interacting across the bond area. So all those tiny forces add up. It's like Velcro, lots of tiny hooks and loops make a strong connection.
Okay, weak but numerous. What's the next step up in force?
Then you have ionic attractions. These are much stronger. Think about table salt, sodium chloride, that's held together by the attraction between positive sodium ions and negative chloride ions.
Right, positive and negative charges.
Exactly. In adhesion, this could be important for how some adhesives, like epoxies, stick to metals. Metals can have surface oxides with ionic character. Adhesives with certain groups, like carboxylic acids, can form these strong ionic or partially ionic interactions with metal surfaces.
Ah, interesting.
The strength depends on the charges and how close the ions are. And this is one reason water can be bad for some bonds. Water molecules can get in between and disrupt those ionic attractions.
Ah, so water interferes with the electrical connection. Got it. What else is holding things together?
Hydrogen bonds are next. These are sort of medium strength.
Okay.
They happen when you have hydrogen atoms bonded to strongly electronegative atoms like oxygen or nitrogen. Think water molecules sticking together. In adhesives, they're important when both the adhesive and the surface have these groups like SOH or NAH groups.
Can you give an example?
Sure. A classic one is licking a stamp. The adhesive on the stamp, often polyvinyl alcohol, has lots of OH groups. The paper envelope is mostly cellulose, also full of OH groups.
Oh.
When you wet it, those groups on the adhesive and the paper form hydrogen bonds. Same idea with wood. Gluing wood is mostly cellulose too, so adhesives that form hydrogen bonds work well.
Clever. Okay, one more type of force.
The last main type is Lewis acid-base interactions.
Yeah.
This is a bit more general. Think of it as electron pair donation and acceptance between molecules. One molecule acts as an electron donor, the base, and the other as an acceptor, the acid.
Okay.
Their strength is related to things like how much heat is released when they interact. Scientists have ways to estimate this. These interactions can be pretty significant in certain...
Okay. Now, you said polymers are key, these long chains. How do chemists actually make them? How do you build these chains?
Right. The process is called polymerization.
Yeah.
Building polymers from monomers. There are two main routes: addition polymerization and condensation polymerization.
Okay, addition and condensation.
Addition is often like a chain reaction. It usually starts with something called a free radical, a molecule with an unpaired electron, which makes it really reactive.
Like an eager Lego block looking for somewhere to connect.
Yeah, something like that. This radical attacks a monomer molecule, adds to it, but the new bigger molecule still has a radical end, so it attacks another monomer and so on. The chain just grows and grows.
Zip, zip, zip.
Pretty much.
Yeah.
You need something to kick off that first radical, an initiator. Sometimes it's a chemical like benzoyl peroxide that breaks down easily. Other times it's a mix of chemicals that react together, like hydrogen peroxide and iron ions that's used in making some acrylics, and in emulsion polymerization, where the reaction happens in tiny water droplets. You can even use things like electron beams to zap the monomers and create radicals directly.
Wow. What about the other ways, not just radicals?
Well, polymerization can also be initiated by ions negatively charged anions or positively charged cations. The trick is keeping those charged ends stable so the chain keeps growing.
And superglue, you mentioned that earlier.
Ah, yes, cyanoacrylate superglue. That's a fantastic example of anionic polymerization. It polymerizes incredibly fast. What kicks it off is actually tiny traces of moisture. Specifically, the hydroxide ions usually present on almost any surface.
Just from the air.
Yeah, or fingerprint moisture. Those hydroxide ions attack the cyanoacrylate monomer, creating a negative charge that then rapidly adds more monomers. The chemistry of the monomer itself helps stabilize that growing negative charge, making it super efficient. That's why it grabs so fast.
That instant stick finally makes chemical sense. Okay, and you mentioned homopolymers and copolymers before.
Right. If your polymer chain is made of only one type of monomer repeating, say, just monomer A, AAA, that's a homopolymer.
Simple enough.
But often, to get just the right properties for an adhesive, maybe you want it tougher or stickier or more flexible, chemists will polymerize a mixture of two different monomers, say A and B.
Okay.
The result is a copolymer, often with A and V units arranged randomly along the chain, like ABBAA. If you use three different monomers, you get a topolymer. This mixing and matching lets you fine-tune the polymer's behavior.
Tailor-made molecules for sticking things. Cool. Okay, so we have the basic chemistry. We know how the polymer chains are made. What are the key properties of these finished adhesives that determine how well they actually work in the real world?
One absolutely critical property is the glass transition temperature, or TEG.
TEG. Okay, what is that?
It's not a sharp melting point like ice turning to water. It's more of a temperature range where the polymer changes from being hard, rigid, maybe even brittle like glass,
Right.
to becoming softer, more flexible, more rubbery. Think about how a plastic dashboard gets softer on a really hot day.
Yeah.
The TEG is crucial for adhesives because it defines the useful temperature range. If you use an adhesive way above its TEG, it might become too soft and gooey, lose its strength, and the bond could fail.
So don't use a low TEG adhesive for something that gets hot.
Exactly. The source we're using, Adhesion Science, actually has a table listing TEG values for common polymers, which gives you a feel for where they might be useful.
Good to know. What else matters besides temperature range?
Another key concept is viscoelasticity.
Viscoelasticity. Sounds complicated.
It just means polymers have properties of both viscous liquids, things that flow, like honey, and elastic solids, things that spring back, like a rubber band. They're a bit of both.
Okay.
Imagine a combination of a spring, which represents the elastic part, and a dash pot, like a shock absorber in a car, which represents the viscous, energy-dissipating part. Polymers behave like systems of these working together. There's a diagram in the book showing this model.
So they stretch but also resist stretching and don't always bounce back perfectly.
That's the idea. Their response to stress depends on time and temperature. For structural adhesives, the kind you want for holding, say, airplane parts together, you generally want them to be mostly elastic, like a stiff spring.
Strong and rigid.
Right. They're often cross-linked to minimize that viscous flow. But for pressure-sensitive adhesives, like on sticky tape, you actually rely on the viscous part.
How so?
That viscous flow allows the tape adhesive to deform easily under just light finger pressure, letting it flow into the tiny nooks and crannies of a surface to make good contact.
Ah, so the gooiness helps it stick initially.
Exactly. And interestingly, you know those faint, wavy lines you sometimes see across an old roll of clear tape?
Yeah. What is that?
That's actually visible evidence of the adhesive's slow, viscous flow over time happening right there on the roll.
Huh. That's fascinating. Okay, so we've got the adhesive chemistry and properties sorted, but what about the surfaces? You can't just slap glue onto anything and expect it to work perfectly, can you?
Oh, absolutely not. Surface preparation is often, I'd say, just as critical as choosing the right adhesive. Maybe even more so sometimes.
Really? Why is that?
Because if the surface isn't clean, or if it's not chemically receptive to the adhesive, you won't get that intimate molecular contact we talked about earlier. You could have the best adhesive in the world, but if the surface has grease or dust or a weak layer on it, the bond will fail at the surface, not in the adhesive.
Okay, so garbage in, garbage out, surface-wise. What are some ways to get surfaces ready?
Well, there are quite a few methods, and it really depends on the material, metal, plastic, wood, whatever, and what kind of contaminants you need to remove.
Right.
The simplest, maybe, is using solvents. Wiping down surfaces with specific solvents can remove oils, greases, fingerprints.
Seems straightforward.
It can be, but solvents have their own issues, health and safety concerns for workers, environmental regulations about disposal. Plus, you have to be careful. Just swishing a dirty rag around might just spread the grease instead of removing it.
Good point. So wiping isn't always enough. What else?
For some materials, especially plastics that are naturally low energy or kind of slippery.
Like polypropylene or polyethylene?
Exactly. Things that adhesives don't naturally like to stick to. For those, you often need to chemically modify the surface. Flame treatment, is one way.
Hitting it with a
A
flame.
controlled flame, yes. It oxidizes the very top layer of the plastic, introducing polar chemical groups like hydroxyl OH or carbonyl CO groups onto the surface.
Making it less slippery, chemically speaking.
Kind of, yeah. Making it more attractive to the polar molecules in many adhesives. Corona discharge is another common method, especially for plastic films and bottles. It uses high-voltage electricity to create a plasma that does a similar chemical modification.
Okay.
There are also newer methods using specialized plasmas or even excimer lasers to tailor surface chemistry.
Sounds high-tech. What about really tough cases like that nonstick plastic PTFE Teflon?
PTFE. That's notoriously difficult. You usually have to etch it chemically to get anything to stick.
Yeah.
One classic method uses a solution of sodium metal dissolved in naphthalene and an ether solvent, THF. It's this really intense dark green solution.
Sodium metal, isn't that reactive?
Very. It basically rips fluorine atoms off the PTFE backbone, leaving a carbon-rich, more reactive layer behind that adhesives can actually bond to. There's another method using sodium dissolved in liquid ammonia makes a cool blue solution that does a similar thing. But yeah, requires handling some pretty reactive chemicals carefully.
Definitely not a DIY job for your frying pan. Okay, what about metals? We glue metals all the time in cars and planes.
Right. And for metals, especially if you need a bond that lasts, particularly in humid or wet conditions, etching is often crucial.
Why, that's
Just cleaning or sanding a metal might give you a decent bond initially. But metals often have thin, sometimes weak, oxide layers, and moisture can attack the bond interface over time. Etching removes weak layers and creates a specific stable oxide structure, often with a microscopic roughness, that the adhesive can bond to much more effectively and durably.
So it gives the adhesive a better grip.
A better, more stable, more water-resistant grip, yes. There's a figure in the book comparing etched aluminum joints to just solvent-wiped ones after humidity exposure. The difference in durability is dramatic.
Okay, so how do you etch something like aluminum?
A common industrial method, especially for aerospace, involves chromic acid, usually mixed with sulfuric acid. It's a whole process, though. First, degrease the metal, maybe with solvent vapor, then an alkaline clean, then the actual etch in the acid bath, controlling the temperature and time very carefully.
Does involve.
It is. Then thorough rinsing, interestingly. Tap water often works better than pure deionized water here, followed by careful drying. And you usually have a limited time, maybe 8 hours or so, to actually apply the adhesive before the surface potentially changes.
Wow. So it's complex and uses hazardous stuff.
Yes, chromic acid etching is definitely an industrial process for high-value parts. There are other etches too, depending on the metal. For mild steel, you might remove rust, degrease, grit blast for roughness, then maybe use hydrofluoric acid, followed by other cleaning steps before priming. Titanium alloys often use an alkaline peroxide etch. Each metal has its preferred recipes.
Lots of specific know-how. You also mentioned anodizing for aluminum.
Yes, anodizing is another level up, especially for water durability. It's an electrochemical process where you intentionally grow a thicker, more controlled oxide layer on the aluminum surface.
Thicker than the natural oxide.
Much thicker and more structured. It's the gold standard for aircraft bonding. In Europe, they often use chromic acid anodizing. In the U.S., phosphoric acid anodizing is more common. The acid is less toxic and easier to handle.
And how does this thicker oxide layer help adhesion? Is it just rougher?
It's not just rougher, it's porous. Especially with phosphoric acid anodizing, you get this amazing microscopic structure, like a honeycomb, sometimes with tiny whisker-like bits sticking out.
Whoa.
This creates a huge surface area and allows the adhesive to penetrate into the pores, creating a really strong mechanical interlock, in addition to the chemical bonding. It makes for incredibly durable, water-resistant bonds. Again, it's a controlled process involving specific voltages, times, and temperatures.
So cleaning, etching, anodizing, getting the surface right is clearly a massive part of the puzzle. What about other stuff like wood, glass, concrete? Do they need prep too?
Absolutely. The methods are different, of course. For wood, it might be sanding to get fresh wood, removing sawdust, maybe controlling moisture content. For glass, it's usually about getting it incredibly clean, removing any organic films or residues.
Fingerprints and stuff.
Exactly. Concrete is porous and alkaline, so you might need sealers or specific primers to deal with that. Composites, being mixed materials, need prep suited to whatever the surface material is, the resin or the fibers.
And briefly, you mentioned adhesion, the opposite, non-stick.
Right. Sometimes you want things not to stick. That's adhesion. Think PTFE coatings or the shiny backing paper on stickers and labels.
Release liners.
Exactly. Those are often silicone-coated papers. Silicones have very low surface energy, making it hard for adhesives to wet them or bond strongly. Designing for non-stick is the flip side of adhesion science.
Okay, so we've cleaned, etched, maybe anodized our surfaces. They're ready. Is there anything else we can do to give that bond an extra boost? That's where primers and coupling agents fit in, right?
Precisely. Think of them as molecular bridges or matchmakers. They help create a stronger, more durable link between the adhesive and the substrate surface.
How do they work? Let's start with primers.
Primers are basically thin coatings applied to the adherent surface before you apply the main adhesive. They can serve several functions, sometimes protecting the prepared surface, sometimes improving the wetting of the main adhesive, and often containing components that promote stronger chemical interaction with both the surface and the adhesive.
So like an undercoat in painting.
That's a good analogy, yeah. And then you have coupling agents, which are maybe even more specific in their action.
Okay, what's special about coupling agents?
They are often these really clever molecules designed to be bifunctional. That means they have two different reactive ends.
Two different jobs.
Exactly. One end is designed to react chemically with the inorganic surface, like glass, metal oxide, or silica fillers. The other end is designed to react, or at least strongly interact, with the organic polymer matrix of the adhesive.
A molecular double agent working both sides.
Kind of. Silane coupling agents are a classic example, especially for bonding to glass and metals. They typically have a central silicon atom. Attached to it are usually some alkoxy groups, like methoxy or ethoxy, which can react with water, and then with hydroxyl groups on the inorganic surface, forming strong surface bonds.
Okay, that's the surface grabbing end.
Right. And also attached to the silicon is an organofunctional group, maybe an Comyn, an epoxy group, a vinyl group chosen specifically to be compatible with or even react chemically with the adhesive being used.
So it grabs the surface with one hand and the adhesive with the other.
That's the ideal picture. In reality, the layers they form can be complex, maybe multiple molecules, thick, not always perfectly ordered. But the basic principle is bridging that organic-inorganic gap. There are lots of different silanes available for different jobs.
Very clever chemistry. Are there other types besides silanes?
Yes. Titanate and zirconate coupling agents are also used. They work on a similar principle of reacting with surface hydroxyl groups. They're often used with mineral sealers added to plastics, but can also treat metal surfaces like aluminum. They don't tend to form the same kind of cross-linked network at the surface as silanes can, though.
Still acting as a bridge.
Still acting as a bridge. Zirconates have some interesting applications, like promoting ink adhesion on treated plastic films. But counterintuitively, certain zirconium compounds can also be used to reduce adhesion.
Reduce it? How come?
Yeah, it's used in paper recycling. You know those annoying sticky labels and bits of tape and waste paper? They call them stickies, and they can gum up the recycling equipment.
Ah, I can imagine.
Adding certain zirconium chemicals during the pulping process can interact with those adhesives and make them less tacky, preventing them from causing problems.
Fighting stickiness with chemistry, that's neat. What about wood? Any special coupling agents there?
Yes, there are specific approaches for wood, too. Wood has lots of hydroxyl groups from the cellulose. So you can use coupling agents that react with those OH groups on one end and have another group on the other end that can react or copolymerize with the adhesive resin. For instance, a molecule with an isocyanate group to react with wood, and maybe a vinyl group to react with the adhesive. There are also systems using modified epoxy hardeners designed to link to pre-treated wood surfaces.
Wow. Okay, well, this has been an absolutely fascinating deep dive into the world of stickiness. We've covered a lot of ground.
We really have.
From just defining adhesion to the chemistry, the forces involved, the polymers.
The importance of getting the surface just right.
Absolutely. The surface prep, and then these clever primers and coupling agents acting as matchmakers.
It really shows that something seeming so simple, like glue, involves this incredibly complex interplay of chemistry and physics at the molecular level.
Yeah, it's definitely not just sticky stuff. Understanding these principles is clearly crucial, not just for aerospace engineers, but it touches so many parts of our everyday lives.
It really does. From the packaging that brings us goods, to the shoes on our feet, to the paint on our walls.
So maybe the next time you peel a sticky note or use some tape or even just see a bug crawling up a window, take a second to appreciate the surprisingly intricate science that's literally holding things together. And maybe think about this. Considering all this molecular complexity we've touched on, what seemingly simple adhesion you see in your own life might have some really intricate science hiding just beneath the surface, something to ponder. It definitely gives you a new way to look at the world, doesn't it? A new respect for the science of stickiness.
Absolutely.
Thanks for joining us on the Deep Dive.